We will take an example from this traditional Indian mirror dish which focuses solar radiation into this cast iron well, and therefore several tons of the cast iron are heated above 400 degrees Celsius. I once wondered what would happen if this hot cast iron hits these 100 tons of sand and stones up to 400 degrees during the summer, and this thermal energy will heat a house in winter. This transfer of solar energy from summer to winter was described in more detail in this my old video on example of heating a house in the Netherlands. Unfortunately, it turned out that these heat losses were large and they took 59% of the energy from this mirror dish, but the remaining 41% of the solar energy completely heated the house. But this video will show the location of our system near Stockholm, and the share of heat losses will be only 40%, and the remaining 60% of the energy from this mirror dish will heat the house completely without other heating sources. So, the heat losses have decreased by 1.5 times, and this fact radically reduces the cost of our system. It was achieved by adding 3 innovations which I will start describing in a minute, and by the climate, because our system works better in more northern climates due to the longer heating season. This is the climate of Stockholm, and its heating season is from the beginning of October to mid-May. These ambient temperatures and this percentage of sunny hours determine this heating needs of a house with an area of 100 square meters and this thermal energy which the 50 square meters of mirrors of our dish will direct into the heat storage. In addition, our mirror dish provides these kilowatt-hours for hot water supply, and these are those heat losses from our heat storage. It is obvious that when this energy inflow from our mirror dish is greater than the sum of this energy outflows, our heat storage is heated in this way from 100 degrees Celsius in March to 436 degrees in September. Otherwise, when the sum of these kilowatt-hours is greater than these kilowatt-hours, the temperature of the heat storage decreases like this. It was the average temperature of this part with these dimensions, which are filled with 96 tons of a mixture of crushed stone, large stones, and sand. In addition, the thermal energy will be stored by these 11 tons of sand, these 8 tons of expanded clay, and these 3 tons of crushed stone and sand. These are the temperatures of all those parts in September, when the heat storage is completely filled with the thermal energy, the complete removal of which leads to these temperatures in March. This thermal insulation with a thickness of about a meter uses the following method of radically reducing these heat losses, which was described in more detail in this my old video. Here the thermal insulation has an air gap, which is a place for installing such a system of air pipes. This circulation of air through the pipes constantly takes heat from the gap and transfers the heat to this water of the home heating system with such power. Its comparison with this required domestic heating power tells us that these months are fully covered, but the rest of the months have this power deficit, which will be covered in a minute. The gap with a thickness of 10 cm will be located here, and those air pipes are located here and here. The heat removal from the gap does not affect this heat loss, but it reduces these heat losses which were described here, and these heat losses decreased almost 3 times in this month and 1.5 or 2 times in this month. But the heat losses of this month outside the heating season do not change. The thermal insulation of the bottom consists of this 50 cm layer of sand, these layers of expanded clay with a total thickness of 1 meter, and these 20 cm of extruded polystyrene foam sheets. This natural soil also adds a little thermal insulation. This is a 10 cm layer of a mixture of crushed stone and sand, where we place such a spiral pipe for circulation of water of a hot water tank during 6 months of summer and autumn. But after that, from the beginning of December, the spiral is used to circulate this water of the home heating system, and therefore the spiral gives the house thermal energy with this power. We see that this power, together with the power from the gap, is not enough to cover this required domestic heating power. This power deficit is covered as described in that old video, which suggested providing heat into the house by circulating air through the cavity of the cast iron well. In addition, here we place this pipe which is used for hot water supply for the remaining 6 months, in winter and spring. In December and January, hot air circulates here and transfers its heat to the water through a small heat exchanger with a capacity of several hundred watts, but for the remaining 4 months this pipe is used to circulate not the air but the water. All these heat extractions for the hot water supply and the home heating radically reduce the temperatures here, and therefore these heat losses decrease during all 12 months of the year and have these values. The higher the cast iron well is located, the higher the efficiency of the mirrors, because this angle is smaller. That is why our heat storage is a tower, and the well is placed near its top. But unfortunately the tower can cast a shadow on the lower part of the mirror dish when the sun is low, reducing the efficiency from November to February. An alternative to the tower is this solution when the heat storage is located underground, and this is a large mirror. It is interesting that an alternative to this one large mirror dish is several smaller dishes which direct solar radiation into one well for all. This is the construction cost of the entire system for solar home heating and hot water supply, and this cost of the heat storage will be explained in more detail later. It's expensive, and it would be nice to reduce the cost by about $10,000 to reach this situation where the economic sense of this our solar home heating becomes equal to the economic sense of these traditional types of home heating. This is the cost of our heat storage, and this cost of its outer surface corresponds to such options based on mesh or polystyrene foam, and it is obvious that it was a country option for similar houses. The location of the system on expensive city land requires more beautiful cladding or burying the heat storage underground.